This is for recording the data605 final projects. We have two problems here. The first one is to generate a random variable x that has 10,000 random uniform numbers from 1 to n. N can be any numbers uh, to choose greater than or equal to 6. Here I'm choosing 10 and generate a random variables y that has 10,000 random normal numbers with a mean of mu equals to theta equals to n plus 1 divided by 2. So to solve the 1.1 question, we need to generate the x and y. I'm using the ron(f) function here, and here is the summary of x and summary of y. As for the probabilities, um, first of all, need to calculate. Uh, so the small letter x is estimated as the median of uh, capital X. So what we do is using a median function to calculate small x, and using quintile function to calculate small y, using a 25 percentage of quintiles, and we got this x and got this y. And first we need to interpret the meaning of these three probabilities. The first one is probabilities that x is greater than its median, given that x is greater than the first quintile of y. And since we already have a random number series, we can just calculate it, and the number, the percent probability is 0.5465. The second one is the probability that x is greater than its median and y is greater than its first quintile of y. This is A and B relationship, and the result is 0.3754. The third one is the probability that larger x is smaller than its median, given that larger x is greater than the first quintile of y. So this is a given by relationship. We can use probability A given by B equals to probability A and B divided by probability B. So we can get the result of 0.4534 here. The second question is investigate whether P larger x greater than x and larger y greater than y equals to p x greater than smaller x times probability that larger y is greater than smaller y, by building a table and evaluating marginal and joint probabilities. So here we're just uh, picking out all the numbers in X that fits all these conditions, and picking out all of those Y's that fitting all those conditions, and create a contingency table and calculate their probabilities, and here is the result. Check to see if the independence holds by using Fisher's exact test and chi-square test, and what's the differences between two, which is more appropriate. So the difference here are the results, and the difference is that the Fisher's exact test is used when sample size is less than 5, and in this case the sample size is 10. So using chi-square test is more appropriate in this case. The second problem for the final project is using the housing price data set from the Kaggle.com and do a series of analysis. First one is the descriptive and inferential statistics. Here I'm just simply using the summary functions, so we can get a distribution of those quantitative variables and We can also get the qualitative variables analysis. Here's the result. The second 2.2 question is provide a scatter plot matrix at least two of the independent variables and the dependent variables. Here I'm using picking the lot areas, GR living area, bedroom above GR, and sales price. And here are the relationship scatter plot matrix for at least for these four variables. Derive a correlation matrix for any three quantitative variables in the data set. So here I'm using the COR functions to calculate the correlations between any two of the three variables. Test the hypothesis that correlations between each pairwise set of variables is zero and provide an 80% confidence interval. So I'm going through each quantitative variables in the training data set and calculate the correlations, and I'm also using a correlation test function and set up 0.8 as the confidence level. If the result is yes, and then I'm returning that this hypothesis result is yes. If it is no, then return no. At the end, I was able to find 6 variables that has no correlations with the sales price. They are the basement's finishing square feet, low qual finish as square feet, basement half bath, MISC value, and years sold. And based on the analysis, I would be worried about the family-wise error because by calculating it, we got the family-wise error rate is 0.737856. This means there's a really high probabilities of committing a type 1 error. Okay, the 2.3 question is invert your correlations matrix from above. Here I'm using the inverse functions to inverse the matrix and multiply the correlation matrix by the precision matrix, and then multiply the precision matrix by the correlation matrix. So we get both the correlation matrix and precision matrix, and then multiply them using the matrix multiply function. And this is the result. We can get an identity matrix. Next is conduct an LU decompositions on the matrix. I'm using the LU function here, and I also did a little bit validation here. Calculus-based probability statistics. So it makes sense to fit a closed from distribution to data, select the variables that is skewed to the right, shift it to the minimum value is absolutely above 0. If necessary, then load the mass package and run fit distribution to fit an exponential probability density function. Find the optimal value of lambda for this distribution and take 1000 samples from this exponential distribution using the value. See here, what I'm picking is the square footage of the unfinished basement. The mean, we can see this is skewed to the right as the mean is 567 and the median is only 477. The minimum is not smaller than 0, so we don't need to shift the data. The maximum value is 2336, and I've already loaded the mass package. Using the fit distribution, we can get the optimal value of lambda is 0.0017629, and we create the sample by using 1000 equals to n. Now, using the exponential PDF, we need to find the 5th and the 95th percentiles using the CD function. Here I'm using this equation, apply fx lambda equals 0.05 to it, then we can get the 5th percentile equals to 29.0956, and applying 0.95 to the fx lambda, and we can get the result that the 95 percentile is 1699. To generate the 95 confidence interval from the empirical data, we're using this function qnorm, apply this 0.975 into it times the standard deviation divided by the square root of n, which is the number of rows of the training data set. And then we can get the confidence interval are these respectively. 544 is the 5% percentile, and 589.9 is the 95% confidence interval. So here I'm listing all the results in just one table. The very end is to do the modeling. First of all, we need to use some type of multiple regression model. Here I'm just using a multiple variables of linear regressions. Before we do it, we need to handle the missing values. So what I did is doing average missing implications by using these functions, and I'm using overall quality, year built, year remodel ad, basement square footage total, first floor square footage, GR living area, full bath, total garage cars, garage areas to train the model. And here is the summary of model. And doing the prediction, I'm using the predict function to predict the sales price of the test data set. And here is the result. The prediction, and I got first entry. My username is Weizo2273 CUNY, and my result is 0.73044.